Huaping Liu, Professor Huaping Liu from Tsinghua University, and his talk is on multimodal active perception.
Okay, Dr. Law, can you hear me?
Yeah.
Okay, thank you very much. Hello everyone, I'm from Tsinghua University. Thank you very much for the organization of this workshop.
Huaping, are you there?
I'm really honored and happy to talk about today. It's a multimodal active talk. First, let's talk about the multimodal perception. Let's start from how we humans perceive the environment. For humans, information about the environment can be perceived by seeing, listening, tasting, smelling, and touching. More importantly, humans are able to unintentionally integrate the perceived information from visual, auditory, olfactory, gustatory, and tactile modalities. Since the olfactory and the gustatory modalities are more about some chemical characteristics, which are beyond the scope of this talk, I would mainly talk about the visual, auditory, and the tactile modalities today. The visual, tactile, and auditory modalities demonstrate different characteristics. For the spatial acuity, the tactile modality is somewhere between vision and audition, worse than visual but better than audition. As to the temporary acuity, the tactile modality again lies between visual and audition, but this time audition is better. In the 1990s, brain science researchers discovered that there are areas in the brain that can process single modality information such as vision, touch, and hearing. In recent years, researchers have further discovered that there are areas within the brain that process multimodal information fusion, and they are particularly interested in processing the fusion between visual, auditory, and tactile modalities. For example, there are visual auditory fusion processing area, visual tactile fusion processing area, and the visual auditory tactile fusion processing areas. However, in practical situations, we do not always use all the modalities simultaneously for perception. For example, we usually look first and then touch or hear. Additionally, we may also need to select different actions to perceive. Here we have work and watch, step and feel, hit and listen. Therefore, it is necessary for us to select modalities and the corresponding actions properly. This arouses the important problem of active perception. I guess all we have this similar experience that what we see is what our brain wants us to see. It indicates that human perception is actually an active process. Here are some Chinese sayings. It means that when your mind is blank, you can turn a blind eye, turn a deaf ear, and the food can even be tasteless. Here, let's see some examples. Sorry. In the first image, we see that the visual modalities provide the global image, but the tactile modality only provides information on local contact points. In the second image, what we see is the bottom of a cup. It is not aligned with what we touch. In the last image, we can see that the data is not paired with different numbers of samples. Therefore, to summarize the challenges for robotic multimodal active perception, we have the first, visual, auditory, tactile multimodal information has different data representation and perception range. The second one, visual, auditory, tactile multimodal information does not have the pairing characteristics of one-to-one correspondence. The third point, the coupling of sensing, perception, and action is highly nonlinear. Considering these challenges, let's talk about the multimodal active perception in details. Here is an overview of the multimodal active perception we proposed in our work. It is mainly composed of two parts. The first part is intermodality. The active perception network is used to actively implement the modality selection. It decides which modalities we will use. The second part is intramodality. An action prediction network is used to actively select actions. For visual modality, we can select different viewpoints. For auditory modality, we can select different orientations. And for tactile modality, different exploration modes can be selected. In the following, I would like to share some of our work in multimodal active perception. For active vision, one representative task is the active object detection. As we all know, great success has been made in the object detection with single view captured image. However, images captured by robots are usually far from perfect. There are problems such as tiny scale, partial view, and occlusion. One image may not contain enough information for object detection. It is expected that the intelligent robot can have the capability to adjust its viewpoint to get better images for detection. Therefore, active object detection becomes a very important perception strategy for intelligent robots. Here we designed a novel deep Q-learning network to generate actions to explore the environment for active object detection. In this video, the children are playing the hide and seek with the robot. With the proposed network, the robot is able to actively find the children. This is an active object recognition task. In many practical scenarios, only one single view is provided, and the viewpoint ambiguity may lead to great challenge for visual object recognition. In this work, we develop a deep reinforcement learning method to actively recognize objects by choosing a sequence of actions for an active camera. The method is realized using the trust region policy optimization, in which the policy is realized by the extreme learning machine. There are experimental results on the publicly available dataset. It can be seen that the proposed active object recognition method works better than random and sequential strategies. There is the active scene description task. Here we regard the popular image captioning, dense captioning, and image paragraphing tasks as scene description tasks. Let's image this scenario. The robot navigates in the room, hoping to find a good location to describe the room. At first glance, the robot captures the image from initial viewpoint. The caption model gives all with the all in all, which is not informative at all. Then the robot explores the room by itself, and a better viewpoint is found to capture a new image. At this time, the generated caption says a living room with a cultured table, which gives more information results. In this work, we propose a framework for active scene description problem, where the intelligent agent is able to explore the environment to find the best viewpoint for scene description. Here are some experimental results in simulator and real scenarios. Okay, the active visual is also useful for robotic manipulation. For example, when the target object in the scene is occluded, the robot can actively explore the environment and change the position of the object until it is suitable for grasping. Similarly, the robot can also rearrange positions of objects by pushing them apart. In this work, a DQN framework is proposed to guide the robotic hand to actively explore the environment until a good grasp affordance map is obtained. We can see from the video that the object that occluded the target object is pushed away first with the learning strategy. Now let's talk about the active tactile perception. One representative task is active tactile object recognition. Tactile sensors are usually fixed on robotic fingers, which can be used to distinguish material texture, roughness, spatial features, compliance, and friction. In this work, a kernel sparse coding method is developed to address the tactile data representation and classification problem. The intrinsic relations between fingers are explicitly taken into account using the joint sparse coding, which encourages all of the coding vectors to share the same sparsity support pattern. The experimental results show that the joint sparse coding achieves better performance than conventional sparse coding. The active tactile perception also can be applied in active terrain exploration. The mobile robots can successfully explore and recognize the terrain by using interactive vibration information. We can see from the picture, for different moving action, the vibration information is also different. Here we have collected 14 different types of terrains, such as concrete, grass, stone, with a Bayesian probability perception method and active exploration behavior. Our method is likely to enable the mobile robot to sense the vibration and decide the next action autonomously. Here are some potential applications. The mobile robot can adjust its driving strategy according to different terrain types. For the flying car, it can even choose to fly mode when it detects that the terrain is not suitable for driving. Okay, in this work, we also use a vision-guided active identification method to perform the waste objects. Okay. The vision guidance module allows the robot to not only detect the desired objects, but also obtain a good grasp of configuration to actively collect tactile data. By classifying the object with this tactile data, the robot can sort the recycling objects into their respective categories by their type of material. It can be seen that when the grasp configuration is not good, the tactile sensors are not able to make contact with the object, although the object is grasped. Thus, it is not possible to acquire effective tactile data. Only when the object is properly grasped, effective tactile data can be obtained. Now let's come to the active perception for audio. As we all know, robots are usually equipped with microphones and cameras to perceive and understand the physical world. Though visual object detection technology has achieved great success, finding the object that makes sounds in the image can provide more semantic information. In this work, we establish a novel robotics sound-indicated visual object detection framework with captured visual and audio information. The sounding object can be detected once the object appears in the room. The active audio can also be used for active localization. In this example, the audio information is used for active localization for the indoor mobile robot. Also, we use the active auditory exploration to identify what's in the bottle. We design different actions to acquire audio information. The proposed learning framework learns to actively select actions for auditory exploration. The target is to recognize what's in the bottle with as few steps as possible. Now let's talk about the multimodal fusion for active object recognition. For different objects, their multimodal perception data has different representation and exhibit different characteristics. What's more, real multimodal data often suffer from significant weak pairing characteristics. In this work, a joint sparse coding method is established for object recognition for the weakly paired multimodal data fusion. Now let's look further into the material perception problem. It is an extremely important but challenging problem for robots. The main difficulties come from the fact that the material properties are difficult to be comprehensively evaluated by single visual, auditory, or tactile modality. In this work, a new active fusion framework for the multimodal material recognition is proposed. The adversarial learning method is leveraged to effectively bridge the gap between different modalities, and the reinforcement learning method is developed for active modality selection. The developed framework and algorithms are evaluated on a publicly available data set and show promising material recognition results. Okay, let's come to the summary. In this talk, we firstly talk about the multimodal perception. Multimodal perception information is complementary to each other. All modalities need to be properly fused for better environment perception. And then we extend to multimodal active perception. It takes the action into consideration. It emphasizes to seamlessly combine the perception with action. In the future, the robot is expected to move from the traditional disembodied perception to the embodied perception, where the robot actively interacts with the environment. At last, I would like to use what the famous American psychologist James Gibson said to close this talk. He said, "We must perceive in order to move, but we must also move in order to perceive." Okay, thank you.
Thank you, I think. Great talk. So far, we haven't seen questions in the chat box. It may come up later, but I do have questions for your talk. So you have used different sensors for your research, like the audio sensors, tactile sensors, and also visual sensors. How do you balance this information from different sources?
Oh yes, you mean how to balance their roles in our task?
Yeah, because you have this multimodal perception.
Yeah.
So you have different information sources, and
Yeah.
you may rely more on vision over touch or audio. How do you determine how to balance this information?
Yes, this is a very important and very very difficult problem. In our preliminary research, we fix their weights for fusion according to our experience and some prior information. But in our about 5 years ago, we developed a series of sparse coding framework for the fusion. One great advantage of this coding strategy is that it can automatically determine the weights for different modalities according to the data distribution. So we avoid this problem by resort the sparse coding method. And now we also hope to use some advanced machine learning method, such as deep learning and the reinforcement learning method, to determine the weight of the different modalities. But I think we need more data sample and more training samples to get these weight values. Okay.
Okay. There's one question to Huaping. How is active exploration incentivized in the proposed approaches? By the reward function of the reinforcement learning, is information gain explicitly measured and rewarded?
Sorry, where can I find the problem?
So it's in the chat box.
Chat. Oh, okay. Okay.
Yeah.
Oh, how is the active exploration incentivized in the proposed approaches? By the reward function or reinforcement learning? Is information gain explicitly measured and rewarded? Sorry, what is the mean incentivized? I don't know the meaning of this word.
I think my inspiration is like your
motivated.
reward. Yeah.
Oh yes. How is the proposal? Yes. We use the reward function of reinforcement learning. We regard the success rate of the grasp as the final reward function, and this will guide the algorithm to select the most suitable strategy for the active exploration strategy.
So in the exploration process, you don't have any rewards. You only wait until the task is successful or not, and then you feedback the reward.
No, we use the final grasp success rate as a reward function.
Okay. So there's
it is yes, implicitly motivated by the yes, you are right.
Yeah.
Okay, thank you.
Okay.
Thank you.
Yep.